All right, in this video I'm going to be talking about double integrals as they are used to compute areas in a plane. Okay, so really I think I need to start off with the idea of the limit of the Riemann sum. I still haven't defined a double integral for you yet, don't worry, I'm going to do that in the next video once we actually talk about some Riemann sums. So, but if we're just trying to develop area, total area is going to be of some sort of region, R. The total area is going to be the sum of our small pieces of area. Okay, so I can just, kind of take it like this, and I could, chop this thing up into various pieces that I knew the area of and add them all together and get myself a decent approximation for the area of this thing. Okay? This is delta area. And if I were to pull this thing out and look at it a little closer, I've got my delta area, and I could compute that by knowing just the width of it and the height of it, because I am assuming that this is a rectangle. Okay, so the value of delta A is equal to delta X, delta Y. Okay, now if I want to actually get an exact value here, I'm going to let this chopping get really fine. Let the number of pieces of area go towards infinity. You know the drill. Area is going to become equal to the integral of delta A becomes dA. Okay, so in the limiting case, dA is going to be dx dy. Also, we could say it's dy times dx. Okay, the difference between those two things, you may go, oh, there's no difference because 4 times 5 is the same as 5 times 4, which is true for real numbers. As to whether or not those are real numbers, that's a different discussion, but you'll see more about the order of integration, I think, in this video. So really the big result is that I'm going to put up here and I'm going to leave up here for the rest of the video, is that if we're computing area, we just need to double integrate dA, just one dA. Okay. Area of region R is given by the double integral over R of dA. Okay, this is kind of just being presented as self-evident. Okay, now the thing is that depending on your R is going to depend, kind of what's going on up here. And so you saw in the previous video that sometimes there's numbers, sometimes there's variables, and who knows what's going to go in these bounds. But what goes in these bounds is really describing R. Okay, and we already found out how to find areas using a single integral last year, so hopefully over the course of this video we're just going to reconcile what we already know with what we're seeing here with double integrals. So, what am I going to do first? Okay, example number 1, rectangle. Okay, yeah, this is a good one. This is going to work like we expected, right? That's always where I like to start, is start with something we can all agree on, make sure our new tool works for that, and then start extending. Okay, so we're going to start with a rectangle here. Okay, so, suppose I've got a rectangle in the XY plane. Not really going to make any assumptions about whether I'm in the positive X, negative Y, whatever. I'll just draw the axes over here. The XY axes, X, here's Y. And what I'll do is I'm just going to kind of label these places. This is X equals A. I'll call this one X equals B. I'll call this one Y equals C, and Y equals D. Right, so I should be getting area is equal to D minus C times B minus A, right? Difference in Y times difference in X. Okay, so this is my region R. And so I should have area is the double integral over R of dA. It's going to be the theme of this video. Okay, but the idea is, okay, well, what is dA? dA is dx and dy. Okay, for this one, it really does not matter. It could not possibly matter any less for this one. But what I'm going to do is I'm going to say, all right, just dx dy. And as far as anti-differentiating, this is like 1 dx dy, right? So what's happening here? X is running from A to B, and Y is going from C to D. Okay, so antiderivative for 1 with respect to X is going to be X. So there's C to D, and I'm just working on the inside integral. So 1 dx is going to be x as x runs from a to b. Okay, and this is going to be b minus a. And what you can do is you can factor this thing out and just run the exact same process, and you would find that it's going to be this b minus a times d minus c. Once you find that the antiderivative of 1 with respect to y is y, and you plug in y equals c and y equals d and subtract it, you get the same thing. So this is going to be b minus a times c minus d, which is what I'd hope to show up in the first place. Okay. For another example, let's look at a triangle. All right. So I think for ease, I'm going to let this be y equals x and y equals negative x. Okay, y equals x, y equals negative x. And then this will be x equals 1. Okay. Now, if this is my region R, and I want to find the area of, area is the double integral over R of dA. Okay. Now, this is interesting because I don't just have a box region, right? I don't have just like number, right? I have number, variables, and variables. So it's like, what am I going to do here? What I'm going to do is I'm going to say, well, the thing that's always in variables is y, at least in this case. And so I'm going to say y needs to be on the inside. Okay. And what you'll see, the more of these you do, the more you'll see that the exterior bounds need to be constant. Okay? Otherwise, it's not a definite integral. Okay? The interior bounds, and when we go to do triple integrals, like any of the interior bounds can be variable. That's completely fine. But the outside bounds, they need to be numbers. Okay? So in terms of x, we're going up to x equals 1, and we're coming from, well, it looks like x equals 0. And then in terms of y, you know, a given slice, and we'll talk more about these slices and the cross sections and stuff in a little bit, probably in the next video more. When I go to do that, I'm going from y equals negative x up to y equals x. And you shouldn't be thinking, wait a second, dude, couldn't you just like integrate f of x equals x minus g of x equals negative x from 0 to 1? It's like, yes, you can. And I'm trying to show you that this is the same thing. Okay, so y equals negative x up to x. And then what I'm going to do is I'm going to take an antiderivative of dy is going to be y equals x minus y equals negative x is going to be okay, this is 2x, antiderivative of 2x, x squared. And that's 1. But that makes sense because this is this has a base of 2 and a height of 1. It's a triangle, so I should expect the area is 1. That's nice. Okay. Just to really kind of hammer home what we were talking about with the area between two curves and last year area volume in Cal BC, I'm going to just draw the old picture. Suppose we've got a function f of x and a function g of x, where f of x is the one that's greater. Right, so let's say that's f, and that's going to be g. And we'll say that this is 1 and this is 9. All right, so, you know, if I want the area of this region R, double integral of dA over R, right? So what we're going to do is we need to actually kind of write this, okay? Well, I've got y equals f of x and y equals g of x. I don't have anything else in terms of y, I just have like 2 x values. So I'm going to need these to be x values here, meaning dx is on the outside, dy is on the inside, and y is running from g of x up to f of x. Okay, and this is becoming the integral from 1 to 9. Okay, the integral of 1 dy is going to be y, from y equals g of x to y equals f of x. And this is what we knew from AP Calculus. Okay. That was one other thing. Now, what if I had gone over here, kind of the next question is, what if I kind of turned this triangle sideways? So that I was looking at something like, pardon me, I need to make sure I'm just drawing this right. So it's going to be, yeah. All right, so y equals x and y equals 2 minus x. This is 2, has a height of 1. It's the exact same triangle as I drew before. I just rotated it. And so this should again come back with an area. But if we took the same approach and we tried to say, okay, y is going to run from 0 up to x, and then from 0 to 2 minus x, that's two different things happening that would require two separate integrals. And that's not, if at all possible, we'd rather just do it in one go. And so I'm going to show you how to do it, right? What we're going to need to do is we're going to need to think about this piece, right? As x runs from, okay, well, if y equals x, then x equals y. And over here, if y equals 2 minus x, then x is going to be 2 minus y. So now I can say that the area of R is going to be the double integral over R of dA. Now in this case, I'm going to want to use dx dy because I've got x being variable. And now I'm going to let, as x runs from the lower to the upper, so x equals y up to 2 minus y. And then over here, 0 to 2. Okay, if I anti-differentiate this, I'm going to get y, or I mean x, as x runs from y to 2 minus y. So I got 2 minus y minus another y, so that's 2 minus 2y. I'm going to integrate that from 0 to 2. dy, and I'm going to get 2y minus y squared. Why did that happen? All right, I found it. I made this same mistake earlier in 6th period. This is dy. Y, if it's y equals x, y equals 2 minus x, this is 1. Okay, so I'm really only running from 0 to 1 and y. And that's why I was not going to get 1 back if I plugged in 2, right? So I'm going to have 2 minus 1 is equal to 1 unit of area. Okay, that makes more sense. All right. I think at this point you might be like, okay, when do I do dx dy versus dy dx, right? Like, it seems like you didn't really have much of a reason to do that besides, you just knew to. And that's true, I did not. So I'm going to kind of just give you the key definitions here. And this is the type of thing that's actually not going to be that easy for me to define. So I'm just going to draw you a picture of it. So if we have a region that is something that we will call vertically simple, and this is pretty easy to remember, vertically simple has vertical lines on it. So if I've got a region that is kind of bounded by vertical lines, say it's that and this is vertically simple. Okay, same way. Maybe this is horizontally simple. And something really weird like that. This is f of y and g of y. This is fine. This is possible. This is something I would call horizontally simple. And the big conclusion here is that if it's vertically simple, then I'm really, at the end, I'm going to be integrating from x equals this to x equals that. So it's going to be dy and then dx. And over here, horizontally simple, I'm going to eventually want to get to y equals this to y equals that. So I'm going to do dx and then dy. Okay, let's see. What else did I want to say on this particular video? Well, I think that's probably about it, besides the issue of like reversing the order of integration, and like why would we even want to do that. I'm going to just kind of tease that, and that's going to be a later video in this playlist. But kind of the question that I took in class was like, hey, I know that the mixed partials are equal. Like if I take the partial derivative here, like with respect to y, and then take the derivative of that with respect to x, it's going to be the same as if I do it with respect to x and then y. Is it the same for integration? If I'm able to do either order, is it going to work out the same? And the answer is yes. Okay? But sometimes there are some integrals that are not going to be able to be done as they're written, right? Let me just go dig one up for you real quick. All right. 0 to 1, 2x to 2. All right, so here's the deal. This thing, you go, you're gonna be like, I'm gonna do this double integral, I just learned how, and we're gonna do it. And you're like, all right, I'm gonna find an antiderivative for 4e to the y squared with respect to y. And then you're gonna remember last year when I told you that like e to the x squared, e to the negative x squared, things like that, there's no hope. You're not gonna find a closed form antiderivative. It's like, oh, that's troublesome. So, but I'm proposing that this would be like the easiest thing in the world to anti-differentiate with respect to x. And then when you do that, something nice will happen and you can use a U substitution, and it's actually not that hard to compute. What we need to do in that case is I'll probably show you how to set it up to reverse the order, but if you're actually interested in doing that, just watch the later video in the playlist. So what I need to do is my kind of advice over here is sketch R. Take the bounds of integration and figure out what they're telling you. Okay. And so, okay, y is running from 2x to 2. Here's y equals 2x. There's 2. Notice it's going from 2x up to 2. So I know that it has to be above 2x. Okay, that was a point of discussion during class. I saw it the wrong way, but I just want to point out it's definitely above here. And x is running from 0 to 1. Well, that would make sense if that's 2. That's just going to be 1 right there. Okay, we can do this. If I needed to reverse the order of integration to get this as, well, I know when I do this, this is going to be equal to, if I switch it to dx and then dy, okay, I'm going to need the y's on the outside. Y runs from 0 to 2. So the question is, what is x doing? It looks like x is starting here at x equals 0. And then this is y equals 2x, so x equals half of y. And what I'll do is I'll just set that up. Okay, x is running from 0 to 1/2 of y. And the integrand is going to be the same. And you might be like, well, why would I need an integrand? And it's like, well, man, just keep watching. I don't think it would be too hard to imagine that if we add an integrand, that'll be like, the volume underneath some sort of surface above some sort of region. Okay, and then this is the type of thing that if you run this through, you can do u du, and it'll work out real nice. Okay, I think that's all I got for you for this video.